So the next talk, and the last one before coffee, is the Cassini Huygens gas chromatograph, mass spectrometer, and aerosol collector pyrolyzer investigations. And the talk is by Paul Mahaffy.
Thanks very much. Also for inviting me. Neither of the investigator leads on the GCMS or the ACP are with us anymore, so I'll do my best to represent these experiments, which of course are two of the experiments on the Huygens probe, two of the investigations. So of course, big day in early 2005 when Huygens landed, and the great success of the mission realized by many organizations and press around the world. So I'm going to focus a little bit more on the mass spectrometer end and the context of mass spectrometer. So why mass spectrometry? Well, really measuring the elemental composition, the isotopic composition, gives us insight into core mechanisms of planetary formation and evolution. How did a planet's atmosphere form, and how is it lost over time? And then, of course, in recent years, with the more focus on, is there life in our solar system on another planet, mass spectrometers are going to be key to that investigation as well. So here's kind of a inventory that my colleague at Goddard, Lu Chao, made, showing the planets and the mass spectrometers that have flown. Of course, a lot of investigation early on with the Russians and so on of Venus probes, Venus orbiter, and a great focus on Mars as well, with the incredible Viking experiment in 1976. Galileo at Jupiter was something I had the good fortune to work on early on. And Saturn, of course, we've been hearing all about Cassini Huygens, and upcoming, as defined by decadal studies, Neptune and Uranus are still to be explored with in situ investigations. And then outside of the planets, of course, comets and moons are interesting. Mass spectrometry, the moon has been supported, and cometary science as well. So the types of mass spectrometer are listed on the right: time of flight or quadrupole mass spectrometers, magnetic sector mass spectrometers, many ways to address sorting out of ions with that type of instrument. So this is a picture view of instruments, primarily from NASA Goddard over the years. And of course, just running through them from top to bottom. We're developing an instrument for the Dragonfly exciting mission upcoming with the quadcopter. Melissa Traynor at Goddard is leading that. We landed our Curiosity lander in 2012, so we've been on that surface for 13 years now, and everything's still working fine with the instrument. We have had excellent collaborations with the Europeans on missions such as MSL, and the next one to the right is the ExoMars MoMA experiment. And I mean, just for an example there, the experiment overall is led by Craig Gosman, and The French team is providing a gas chromatograph for that experiment, and we're providing a new type of mass spectrometer, an ion trap mass spectrometer, which can do things that the previous quadruples could not do. For example, if you're looking for life and you do laser desorption, you find a complex molecule, then you can deconstruct it in an ion trap mass spectrometer. And the question is, can only life make a very, very complex molecule? And so that's one thing we'll try and do both on Dragonfly and on the Rosalind Franklin lander. LADI mass spectrometer around the moon. Of course, to the right of that is a Galileo probe mass spectrometer. And on the bottom, the MAVEN mass spectrometer is still orbiting Mars. And the Cassini GCMS we'll talk about today. So that was a picture version, and here's the list of instruments that have primarily been produced from Goddard over the years. And it started way back up at the University of Michigan, where Hasso Niemann went to graduate school and teamed with Nelson Spencer and George Kerrigan up there. And they flew a lot of upper atmosphere experiments, basically using rockets left over from the war and looking at what the upper atmosphere was made of, eventually learning how to measure winds and temperature in the upper atmosphere using scanning baffles or rotating, spin rotating mass spectrometers. And that was then followed by, there was enough of that data that Al Hadin made kind of a semi-empirical model of the upper atmosphere winds and temperatures. You could dial in any altitude and any season and basically understand a prediction of what the composition would be. Then Hasso got more interested in focusing on planetary mass spectrometry. So his first mission was the Pioneer Venus Orbiter, which measured the composition and scale height temperatures of the upper atmosphere of Venus. 1989 to 95, the Galileo probe mass spectrometer. And I came to Goddard in 1980, so I worked on that a fair bit with Hasso. The Cassini orbiter ion and neutral mass spectrometer was, and then the Cassini Huygens probe. Interesting story there was the announcement for Cassini came out both with an opportunity for an orbiter mass spectrometer and a Huygens probe mass spectrometer. And Hasso, following his experience with Galileo probe mass spectrometer, was primarily interested in doing probe science. And so he kind of declined to propose a mass spectrometer for the orbiter. So there was one proposal which went in, which he won. I think Jonathan was a co-I on that mission. And then headquarters actually got no selectable proposal for an orbiter mass spectrometer. So they came back to Goddard and said, well, will you guys be willing to build an orbiter mass spectrometer? And after some thought, we all said, sure. And then a science team was selected with Hunter Waite and Wayne Kasperzak and Roger Yell and others leading that science. And so it did wonderful things, of course, which you'll hear about from Hunter, both at Titan's upper atmosphere and Enceladus. A couple of instruments in red there, which were not successful. Nozomi mass spectrometer on a Japanese mission was lost in space, as was Contour. When I came to Goddard, my first job was, there was a Comet Rendezvous asteroid flyby mission in the works, and how do we optimize both a closed and an open source for cometary missions. And so we developed basically an ion switch. So we would have an optimized open source and an optimized closed source. In a closed source, you basically can get a RAM enhancement of the density. We have lots of collisions in the source, so you can't necessarily measure ions or reactive species. And so we developed that for CRAF, but then we incorporated that on other mass spectrometers such as INMS, MAVEN mass spectrometer, LADI, and so on. And MSL, of course, took a lot of effort to develop a very complicated experiment, but there also we had terrific collaborations with the Europeans. They were part of the, very much integrated into the team. They worked on the gas chromatograph aspects of that experiment. We had 6 columns, and they were responsible for that. We did operations both at JPL, and 1 week out of the month we would do operations out of Toulouse with the GC team. So that's ended up being a very exciting collaboration. We've had a regular set of French postdocs in our lab at Goddard. And then in blue are things that are not yet realized. The MoMA mass spectrometer for ExoMars is delivered and ready to go. Again, it's this ion trap mass spectrometer where you can do both chromatography and laser ablation mass spectrometry and look for very high molecular weight species. We calibrate with a peptide, for example, over 1,000 Daltons. And DRAMS for the Titan Dragonfly mission is sailing through its critical design reviews and such. So it's well on the way. After many years of proposing Venus missions with various people, some of them in this room, a mission was finally selected that Jim Garvin at Goddard is leading. And so that's a probe where it's been a very long time since there's been a Venus probe at Goddard in planetary science. And so this will be exciting. Its development is going fine. And then basically a Mosaic GDC mission. Some of this is still up in the air with the turmoil at NASA, but we were selected for Earth orbiting mission with multiple mass spectrometers to look at the upper atmosphere here. So that's kind of the big picture. And I talked a little bit about some of the motivations for these experiments. And again, multiple types of mass spectrometry. You can do time of flight mass spectrometry. This has been developed for various missions. The quadrupole mass spectrometer, basically you send ions down a set of 4 rods, hyperbolically shaped rods. And if you solve the equations of motion, basically you get 2-dimensionless parameters, A and Q here. One's proportional to the DC, the other to the AC. And so if you scan the amplitude of those voltages, basically you can find a region where the ions are stable. They don't just basically hit the walls of the rods. And so typically for these mass spectrometers, what we do is, in order to save on data bandwidth, we go to the center of the peak, try and make the peaks of the mass spectrometer as much of a step function as we can, go to the center of those peaks and basically count the ions that come out the other end of the quadrupole. So this is the GCMS. Of course, with going into a deep atmosphere, you have all sorts of pumps you need. You have valves that you need to introduce the gas, send the gas to the right place, and so on. And so the mass spectrometer is in the bottom, the quadrupole mass spectrometer, the detector at the end. And then for GCMS, the whole set of electronics and the getters and the valves and so on are all enclosed in a housing, so you don't get any passion discharge with the changing pressures as you go down. And so on the right is basically the electronic center are stacked around the mass spectrometer. So again, I mentioned that I had developed this ion deflector for craft mission, and we later used it as a switch to either get an optimized closed source measurement. Upper left, you can see for the RAM enhancement of the density in that source basically gives you better sensitivity. or an open source where you can also measure ions, or you can measure neutrals, which are directly ionized without any wall collisions. And so Hasso Niemann thought that was a good idea. So he basically took 4 of these deflectors and stacked them all together, and trying to avoid contamination of one source from another source. 3 of these sources were dedicated to GC analysis, 1 was dedicated to ACP analysis, and 1 was a direct atmospheric sampling. And so that all worked, but clearly the most successful measurement, I would say, of all this very ambitious set of experiments was the direct sampling of the atmosphere with ion source 1. So there's the inlets and the outlets. Basically, the inlet at the stagnation point of the probe, sticking out. The experiment, the inlets were covered, and then they were actuated by pyrotechnic actuators. In fact, in building 21, where the mass spectrometer was developed, the folks would test the pyros for the inlets on the roof of the building because they didn't want them to shoot straight down. They were afraid that the probe would catch up with the pyros and pyro caps and do some damage. So they fired them off on from the top of the building. And this is a somewhat complicated gas flow schematic showing the mass spectrometer, the ion sources, all the valves, and the interface to the GC inlets, and so on. So a lot of technologies were adapted from commercial vendors for this work. These are all the companies that contributed detectors or valves or other components that were all integrated at Goddard. I would say the chief interface of these folks was Dan Harpold, who since retired. And the chief system engineer on the electronics was John Maurer, who was an incredibly talented guy, had his hands in most of the planetary or Earth orbiting mass spectrometers that were ever flown. He passed away recently. And there's Hasso and one of his chief sidekicks, Eric Rahn, who's still at Goddard, who would help him basically tune the ion sources, optimize the lenses, get the maximum focusing and such. Here the mass spectrometer is hooked up to lab electronics, KNet crates, and dozens of wires coming out to interface with the GSE there. And so here's a diagram of the ACP interface. Basically, the ACP was designed to get a metal filter out into the atmosphere at different altitudes and then retract it and heat it up to different temperatures and then send the gases over to the dedicated ion source in the mass spectrometer. And so here's a descent sequence, basically, as you go down into the atmosphere, showing the times when ACP samples were taken, showing times when 1 of 2 leaks into the direct inlet of the mass spectrometer was taken in the middle, and so on. So it was all pre-programmed descent sequence, which was exercised successfully at Titan. And here's a couple of spectra. The top one basically is in the 10 to 20 kilometer altitude. That's an average spectra, basically showing nitrogen and its isotopes over in the mass 28 region, and methane and its isotopes at 16, 17 and below. And then, as was mentioned by Jonathan, at the surface, sitting on the surface, the instrument was still working and still transmitting data back to the orbiter for quite a while. And other species, interesting species, showed up from the surface and listed there: acetylene, vinylbenzene, propane, butane, and so on. Noble gas experiment basically set limits on the heavy noble gases and measured argon-40 from the interior of, produced ultimately from the interior of Titan. And ACP GCMS reported results were not without some controversy. A paper was published by the ACP lead some time after. Complex organic matter in Titan's atmosphere, atmospheric aerosols from in situ pyrolysis and analysis. And that was vigorously contested by Klaus Biemann, who had issues both with the interpretation of the mass spectra and suggested that if ammonia and HCN were detected, some of the other products, lower molecular weight organic, should have shown up in those spectra as well. And the GCMS team responded to that. So that was interesting. So I'll end here with Hasso Niemann's summary of GCMS ACP investigation at the, this was the third International Planetary Probe Workshop. His summary slide of what he thought were the main results, basically showing the increase in methane mole fraction near the surface. Again, methane and nitrogen were measured very, very well all the way down. Primordial noble gases, argon measured, and upper limits for krypton and xenon. And on the surface, ethane, carbon dioxide, and cyanogen detected and landed on an organic rich surface. So that was also a summary of the GCMS investigation. And so that's it. I put, if this gets posted, I put a lot of a slide for each of the other planetary missions in the backup as well.
Thank you very much, Paul. Again, we have time for a couple of brief questions.
So, Paul, you didn't mention Neon 22. You know, there's Neon 22 measurements. There was at least some preliminary reporting of Neon 22. And
the trouble, sorry. The question was Neon 22 measured or not. The issue with Neon and a unit resolution mass spectrometer is that you get an interference from the doubly charged CO2 and doubly charged argon-40. And so all those isotopes are only measured well if they're in sufficient abundance. So I have not seen any, so a limit certainly could be established, but not a measurement.
Yeah, just for completeness, although it didn't really do anything at Titan, it's worth mentioning there was a second mass spectrometer on the Cassini orbiter, which was the cosmic dust analyzer, which was time of flight mass spectrometer that also had some very interesting results at Enceladus, obviously, and the rest of the Saturn system. So Cassini and Huygens together were remarkably well equipped with mass spectrometers, 3 of them in total.
Yeah, and I think Hunter's going to talk about INMS data, right?
Okay, well, thank you very much to Paul. And in fact, so thank you to all of this morning's speakers. We have a coffee break now. We're talking about the talk that was left over from yesterday evening. I think it's, yeah, last talk of this morning. This is called real-time planning. I think We're in need of coffee, Athena. Yeah. Okay, so we will reconvene at 11:15.